Good morning, everyone. I hope you're all doing well. So it's the final stretch. We have 4 more weeks and we're done. This goes by fast. So we're continuing today with rigid body kinematics. Okay, so if A and B are two material points on a rigid body, then we know we can relate their velocity and their acceleration. And you can also relate their accelerations. And then we also looked at if we have a point moving relative to a rigid body or a point moving to a rotating frame. What are omega and alpha? They're the angular velocity and the angular acceleration of the rigid body, and they are properties of the rigid body. So say that I have a rigid body and I have 3 points on it, A, B, C. If I'm doing the velocity analysis, so again I have a rigid body and I have 3 material points on it, A, B, and C. A, B, and C. If I'm doing the velocity analysis between A and B and A and C, will I use the same angular velocity and same angular acceleration? Yes or no? Yes, right? Yes, because they are all material points on the same rigid body, and the angular velocity, angular accelerations are properties of the rigid body. Okay? Now here, which term is the Coriolis term? Coriolis acceleration. 2 omega cross, so this is the Coriolis acceleration. Can anyone give us an example where this case applies? Either a rotating frame or a material point moving relative to a rigid body? The merry-go-round, right. So if you have a ball moving relative to the merry-go-round, you can write the velocity of the ball relative to the velocity of some point on the merry-go-round using this equation. Any questions? So for planar rigid body rotation, say I have a bar, some bar, okay? And I can, say I have some bar, I have some co-rotational bases attached to it. Rotational bases, fixed bases. If I look at this tensor, what is this tensor? Yes, but further, what does it mean? Yes. Did you have an answer? No. Okay. Yes.
Rotate the bases to the fixed bases, so that correlation to x.
Close, but how do we make sure? How do we know what the tensor does? The action of a tensor is defined by what it does to a vector, right? So let us consider a vector. Let me consider a vector u. Plus uz easy, and I'll apply qu. And I remember the definition of the bond product, A bond B applied to C is B dot C along A. So then here, what do I do? I'll take this term, multiply it by this term. I'll get, will I get 0 or non-zero term? Non-zero. What is it going to be? Ux, small ex, right? Okay. What about Ex, bond Ex applied to Uy, Ey? That's going to be Ex dot Ey, which is 0. Same here. So we're going to be left with, can anyone tell me what we're going to be left with? Uy, small Ey. Okay. Make sure your neighbor gets this answer, and let's think, based on this, what is the tensor Q? What does it do? Take 2 minutes, make sure you chat about this with your neighbor. Okay, so any questions about these calculations? Okay, what does this tensor Q do? Okay, yes. Not the basis, yes, but by doing that, what does it do? A little bit more detail. You're very close. Yes. it rotates a vector, right, from the reference configuration to the current configuration. Or it rotates a vector from being, remember we said that when we have, or let me do this, okay. So we could have the reference configuration of the rigid body, and we could have a corotational vector in that reference configuration, or a vector between two material points on the reference configuration. Now this vector is expressed in the Ex, Ey fixed basis. The components of this vector on this basis are the same, except that the basis vectors are different, right? So this vector V, I can write it as A Ex plus B Ey. And over here, I can write it as A small ex plus B small ey. So what this tensor does is that it takes this vector and rotates it to that vector. So it's a rotation tensor that takes a vector from the reference configuration to the current configuration. Here, Q. Okay. What is the angle theta physically in this figure? Exactly, the angle between small ex and big Ex. So this is theta here. So the angular velocity can be written here as theta dot Ez, where theta is some angle that the rotational basis, or some angle that any material line on the rigid body makes with some fixed reference line. So for example, if I go to the I want to go to the last problem you had on your midterm, which looked like this. And I think you were given the angles here, theta, gamma, I think it was epsilon, here. And I had A, B, C, D. How can I write the angular velocity of link AB in terms of the rate of change of some angle? So I know that omega AB is some value along EZ. What is this value? I want to write omega AB as the rate of change of some angle. Theta dot, right? Because theta dot is the angle that bar AB makes with some fixed reference, which is here the vertical. What about bar BC? What is the angular velocity of bar BC in terms of the rate of change of some angle? Epsilon dot, right? Say here I had the angle beta. Would omega BC equal to beta dot? No, why not? Yes, because beta is not the angle between BC and some fixed line. It's the angle between two moving lines. Does that make sense? Any questions? Yes. Yes, that the angular velocity of a rigid body that is rotating in the plane is the rate of change of the angle that any material line that the rigid body makes with some fixed reference line. Maybe I'll write that down. the angular velocity of a rigid body. I'll call it the angular speed. Okay, so the angular speed of a rigid body rotating in the plane is equal to the rate of change of the angle between any material line on the rigid body. For example, bar DC, any material line on the bar DC is the line itself. It's the rate of change between this material line on the rigid body and any reference line that is fixed. So that could be gamma, the rate of change is gamma dot, but I have to take into account the signs too. Now the angular velocity for a body that is rotating in space is more complicated. You would learn about that in intermediate dynamics. Any questions about this? Is that clearer? Great.
Material line between 2 points on the body?
Yes, a material line is any line between two material points on the rigid body. And why do I say any line? Because say I have a rigid body that's like this. Okay, I can consider this line or I consider this line. The angle between these two lines is constant. So when I look at the rate of change between these two lines and any fixed reference line, the difference is going to be constant. Its rate of change is going to be 0. So if I look at this line here and this line here, if this is alpha, this is pi by 2 plus alpha, the rate of change of these two angles is going to be alpha dot. So it's the same, no matter which material line I think of or I consider on the rigid body or any fixed reference line in space, in the plane. Does that make sense? Okay, cool. Questions? Our new topic of the day is rolling and sliding. Okay. When you drive a car, raise your hand if you drive a car. Drive, yeah? Okay, most of us drive. When you're driving, do you want the car to roll, pure roll, or do you want it to roll and slip? Roll. Why do you want it to roll? The tires, yes.
What if you're drifting?
If you're drifting, then you want it to slip. Then it's slipping, right? But what's the problem with drifting? Do you have full control when you drift? No. You're losing traction with the ground, right? Also, when you're slipping, so say you're driving on ice and you're slipping, you press the gas on, you stay in your place. You don't move as much as you should. So really when you're driving, unless you're having fun, ideally you don't want to slip, you want to roll. Rolling a wheel or a rolling happens when the velocity of the contact point between the wheel and the ground is 0. So there's no slip speed between the wheel and the ground. So if this ground is fixed, the wheel is rolling if Vp is equal to 0, where P is this point, P, point on wheel or disc So Vp is equal to 0 if you're rolling. In O'Reilly's notation, they call it rolling and sliding. In Merriam-Craig, they call it roll without slip to signify pure roll, and roll with slip to signify some roll with some sliding. So I'll be clear in the exams, but you can say roll, pure roll, slip, roll without slip, or roll with slip. Okay. Is P a material point on the disk? No, why not? Yes, the material point that is P changes as the wheel rotates. So if I take a wheel, I do not have a wheel, but if I take a wheel, oh, I have this. Okay, so if I take a wheel, and this is point P at this instant, this is the material point that is P at this instant. Once the wheel turns, the material point that is P has changed. So P is not a material point on the rigid body. Where is the instantaneous center of rotation of a rolling wheel? What do we think? Take a minute, chat about it. Where is the instantaneous center of rotation of a rolling wheel on a fixed surface? Okay, so what do we think? What is the IC for this wheel? P, right? Why? Yeah, it's the point on the wheel which has 0 velocity at this instant, which is P. Now, at this instant, the wheel is rotating about P. So if I were to draw the velocity profile of this wheel, it would be rotating about P at this instant. Points at the same radial distance from P have the same speed. So the wheel at this instant is rotating about point P. Vp is equal to 0. However, so P is equal to the IC. However, the acceleration of point P is not going to be 0. Same as the IC. If the IC is not a fixed point, its acceleration is not going to be 0. I have a question. Say I have, well, do you have any questions first? Say now I have a disk on a truck. So the truck is moving with some velocity, and I have of the truck, and I have a disk on the back of the truck. How can I what is the condition, mathematical condition that says that the wheel is rolling without slipping on the back of the truck? So for example, if the wheel is rolling without slipping on a fixed surface, then VP is 0. What about for the wheel on the truck bed? What is the condition, mathematical condition that is equivalent to saying that the wheel is rolling without slipping on the truck bed? Take a minute, think about it. Point P on wheel. Yeah, point on wheel.
But at every time instant, the location changes.
It's always the point on the wheel that is in contact with the ground, but the material point on the wheel, that is P, changes. So this is rolling. This chalk is always going to point towards P, but the material point, that is P, changes. Okay, so what do we think? How can we express the fact that, or how can we express it when the wheel is rolling without slipping on the moving truck bed? Yes? VP is equal to VT, exactly. So what I'm going to do is I'm going to take the truck bed, the wheel, I'm going to consider 2 points, P and Q, and I'm going to say that VP is equal to VQ. If P, or if the disk is rolling okay, so if VQ is 0, the disk is on a stationary surface, and this just means that VP is 0, we recover this case. If not, if the disk is rolling without sliding on a moving surface, then the velocity of P, the velocity of Q should be the same. What are P and Q? They are the point on the disk. P is the point on the disk that is in contact with the surface, and Q is the point on the surface that is in contact with the disk. Okay? Let us try to determine the acceleration of point P. Okay. So I have the wheel on a fixed surface called point P, point Q, the center of mass C. The angular velocity of the wheel is okay. So I can say VC minus VP is equal to omega cross XC minus XP. C is the material point on the rigid body. P is the instantaneous center of rotation. So what is VP? 0, right? What is VC? What is the direction of VC? The velocity of the center of mass. Right. What is it? Yeah, it's horizontal. It's the only point on the rigid body that is moving in rectilinear motion. It's going on a straight line. All other points are going on curves. So XVC okay, so VC is x dot EX is equal to omega EZ. What is XC minus XP? R-A-Y. R-E-Y, and that's omega r minus Ex. Okay, so no contradiction. I did obtain that VC is along Ex, and I can project to get X dot is equal to minus omega r. So this is the speed of the center of mass. I can take the derivative of this equation. What will I get? Yeah, X double dot is equal. Okay, then I'll use my velocity, my acceleration analysis. Okay, now I can replace a few terms. AC is equal to X double dot, which is minus alpha R Ex. Minus AP is equal to alpha EZ cross XT minus XP. We said that's equal to REY plus EZ cross EX is EY, right? Okay. What does this mean? What is AP here? AP, so this term and this term are the same. AP is omega squared R EY. So the acceleration of point P is going to be vertically up, right? It's not zero, it's pointing vertically up. Any questions? So yes, we have to be careful. AP is not zero. Yes?
How come the acceleration is only upwards and not going to the acceleration as well? Because it's rotating, right? So wouldn't like...
It is rotating, but at this instant, it's instantaneously rotating about P. Right? So you need to think, if you think about it, okay, so the calculations show it, but if you think about it intuitively, point P is not sliding like that way. It's going pure up. What is it?
Is it basis like moving with
What basis?
or
So I'm rolling, and this point is elevating rather than elevating and slipping. So the acceleration is purely upwards. So in other textbooks, they explain this differently. While I pull up a video, please do set 17 problem 3. Set 17 problem 3. Okay, so the way other people or other textbooks explain it is that when you're rolling without slipping, imagine you have a disc that is deposited in, or that has paint on its rim. When you're rolling without slipping, the amount of paint, the length of the paint segment you deposit on the ground is equal to like the length, the circumference of the circle kind of thing. So for example, if you have a circle, radius r, circumference 2 pi r, once the circle does a full turn, if you're rolling without slipping, the length of the paint deposited is 2 pi r. Does that make sense? So it's like having a roll of tape and depositing tape on the ground. If the roll of tape is rolling without slipping, then the amount of tape deposited is going to be the kind of how many, the angle of angular displacement times the radius. So like this, let me see. You've seen this before. So in this situation, the length of tape deposited is the length of the tape deposited is the angle of rotation, the total rotation angle times the radius. And in this case, you would be rolling purely. If you would be slipping, then the tape either has to break or you have to deposit a lot of tape at the same location. Yes, so in this case, imagine the tape is directly on the ground, that's pure roll. If the tape could stretch or compress, then you would have kind of slip. Okay, so they explain it this way. I have a disk. Okay, not my best drawing. Let me fix it. Okay, I have a disk. Say I'm going to rotate the disk by the angle theta. Then this length, which is equal to what? If the disk has radius r, what is this length equal to? This portion here. What is that equal to? Yes. R theta, right? If the disk is in pure roll, then when I rotate by an angle theta so that this point is on the ground now, point B is on the ground, this distance traveled is going to be equal to r theta if the disk is undergoing pure roll. So this distance is r theta, meaning that also this distance here between the two centers is r theta. if I call this distance s, then they say that s is equal to r theta, and s dot is equal to r theta dot. So for a lot of the solution manuals you see on the internet, not that you're looking at solution manuals at all, you should not be, but if you were to, that's their starting point usually. S is equal to r theta. Notice though that there's a sign difference between r s, their s dot is equal to r theta dot and r x dot is equal to minus omega r. There's a sign difference because when you're rolling along negative Ez, you're advancing along positive Ex. So when you're doing this, you have to be careful of the signs, whereas here they're automatically taken care of. So usually what I want you to do is to do that up there. I think it's just not easier, but more systematic. Any questions? Questions? Okay, so continue with problem 3 of the set, 17. Okay, so the rear driving wheel of a car has a diameter of 26 inches and it's an angular speed of 200 rev per minute on an icy road. If the instantaneous center of zero velocity is 4 inches above the point of contact of the tire with the road, determine the velocity v, the speed v of the car, and the slipping speed vs of the tire on the ice. So we have this tire, we're given the location of the IC 4 inches above the ground, the diameter, the angular speed, we need to determine the slip speed and the speed of the center of mass of, or the speed of the car. The speed of the car. Okay, so what do we do? Ideas? Yes.
Can we take the 4 inches and then kind of expand it out to the radius of 13 inches of the wheel to find the radial velocity of the automobile?
How?
I guess I'm not sure on the formality for this, but my intuition says we take the angular velocity and then multiply by the radius of 13 inches. So it's kind of like a ratio thing, times 13 inches over 4 inches.
Why not just use the equation, velocity analysis, between the IC and the center of the disk, right? Then the velocity of the center minus the velocity of the IC is equal to what? Omega of the disk crossed with XC minus XIC, exactly. And what is the velocity of IC? 0. Omega is given, the distances are given, so we can find VC, right? We can find our unknown VC. And then if I want to, any questions? That makes sense? What do I do if I want to find the slip speed? What is it? Exactly, because the slip speed is the velocity of this point. I'm going to call it P. So the slip speed is Vp minus Vic is equal to omega xp minus xic. And again, I have everything I need. I can determine Vp. That's it. So what do you think the direction of the slip speed is going to be? Along positive Ex or negative Ex? If I take Ex anywhere like this. What do you think the direction of the slip speed is going to be? Negative, right? So the IC is here. The car is going to the front. And this wheel tire is slipping to the back a little bit, Vx. So I can draw the velocity profile like this. Make sense? Yes. Mm-hmm.
Would the omegas both be the same because they are both on the same wheel?
Yes. Yes, exactly. So P, the IC, and the center of mass, they all behave as material points on the same rigid body. Any other questions? Okay. I want to move to a different topic. So any questions before we move on? Okay. Then I'll erase it. Okay, so remember our master plan for the class. We started by looking at a particle, and we did particle kinematics and particle kinetics. So in particle kinematics, we looked at the position, velocity, and acceleration vector, kinetic energy, angular momentum. Then for the particle kinetics, we looked at the balance laws, balance of linear momentum, balance of angular momentum, the work energy theorem, and the linear impulse linear momentum equation, angular impulse angular momentum equation. So all of this we did for a particle, then all of that we did it again for a system of particles, and we want to do the same thing now for a rigid body. So before we are able to formulate the balance laws for a rigid body, we need to finish up formulating the kinematics. So we've done the velocity, the acceleration analysis relating to material, the velocities and accelerations of two material points on a rigid body, or a point that is moving relative to a rigid body. Now I want to go back and figure out what the center of mass of a rigid body is, linear momentum of a rigid body is, angular momentum. And when we look at angular momentum, we're going to introduce the inertia tensor. Have we heard of moments of inertia? So we're going to introduce that to calculate the angular momentum of a rigid body, then kinetic energy, and so on, so that we can formulate the balance laws. Before we do that, you guys take a 3-minute break, go, small walk, come back in 3 minutes. Okay, so we're going to look at the rigid body as composed of differential masses dm, right? So previously we looked at the system of particles, and how did we calculate the center of mass for a system of particles? The sum of Ri mi over the sum of mi over the total mass of the system. How are we going to calculate the center of mass of a rigid body? So for a system of particles, we said that RC is equal to the integral of, it's the sum of Ri Mi over the sum of Ri. I equals 1 to m. For a rigid body, instead of summing, what are we going to do? We're going to integrate, which is a continuous sum. So for a rigid body, xc is equal to the integral of r dm over the integral of dm over the body. So this is the whole body. It's composed of the differential masses dm. I have my origin here. Each differential mass dm has a position vector r. Right? So each portion dm of the body has position vector r, and I'm summing over all the dm's, differential masses dm of the body, times r divided by the total mass of the body to get the location of the center of mass. Okay? So r depends on the material point. R depends on this differential dm, right? If I were to change dm, r would change. How do I calculate the linear momentum of a rigid body? How did I calculate the linear momentum of a system of particles? What was the linear momentum of a system? Exactly, the sum of the linear momenta of the individual constituents. So how do I calculate the linear momentum of a rigid body? The integral of what? Exactly, of V dm over the rigid body. Okay, so what is V? V is the velocity of the differential mass dm. So if I were to consider a different V, a different dm, I would have a different V. Okay. Now here I can write that Vc is equal to the integral over the body of d by dt of r dm over the total mass of the body. Which I can write as integral over the body of V dm. Am I allowed to take this derivative inside the integral? Yeah. You can read more about that in Orari's textbook. But usually when you're taking a derivative of an integral and the boundary of the integral is changing, then you have to use Leibniz's rule to take into account the derivative of the boundary of the integral plus the derivative of what's inside. Here we do not need to do that because we're considering the material kind of boundary, the set of material points rather than a moving boundary. Okay, so this to say that I can write G in terms of the linear momentum of the center of mass. How? How can I write the linear momentum of the rigid body in terms of the linear momentum of its center of mass? Yes? Right, exactly. The total mass times Vc, right? Where the total mass is the integral over the body of dm. Okay, so far for rigid body we have the position vector of the center of mass, velocity, we can calculate the acceleration of the center of mass, the linear momentum. Any questions so far? Yes. Sorry, it should be mi. Thank you. Thank you. Any other questions? Questions. Okay, what's next? Angular momentum. How do I calculate the angular momentum of a system of particles about any point P? About any point P. Exactly. Ri minus Rp. Okay, and how will I do that for a rigid body? What do I do? Yes.
RC minus RP cross with
Yes, for a rigid body, the angular momentum about point P, it's the same thing, but I will integrate. So integrating over the body of R or X, I'm using R, R minus RP cross V dm. So again, I have a differential mass dm. Its position vector is R, its velocity vector is V. So R and V depend on dm, and I'm summing for all possible dm's in the body. For the set of all dm's in the body, I'm summing this R minus Rp cross V dm. Now, does Rp depend on dm? No, right? No, it does not. Okay. If I want to calculate the angular momentum about point C, the center of mass, then that's just equal to what? The integral of what? R, guess what? There's a term before the cross. So if I want to calculate the angular momentum about the center of mass, what is it going to be? R minus RC or R minus XC? I'll call this RC. Okay, and if you remember, we did a few kind of relationships between HP and HC for the system of particles. We're going to do the same for the rigid body. So if I consider HP is the integral over the body of R minus Rp So I'm maintaining the equality. I'm adding RC, subtracting RC. Guess what I'm going to do next? Can anyone guess? Mm-hmm. Yeah, expand, exactly. Or factor out. So integral over the body of R minus RC plus V dm plus the integral over the body of RC minus Rp plus V dm. Okay, how does this expression simplify? Exactly, the first term is HC. So this is the same as HC up there, plus So this RC minus RP, does it depend on dm? No, right? C and P, their locations do not depend on the particular dm I'm considering. So I can take this term outside the integral, RC minus RP crossed with the integral over the body of V dm. What is the integral over the body of V dm? Yeah. So I have now that HP and we should have had the same relationship. We should have had the same relationship for a system of particles. Okay, so now the issue is, do I have to evaluate an integral over a randomly shaped rigid body every time I need to calculate its angular momentum? Hopefully not. Hopefully I do not need to calculate an integral over a rigid body every time I need to calculate its angular momentum. So we're going to try to play with the expression of the angular momentum a little bit so that we will see what happens, but hopefully we don't have to integrate every time we want to calculate the angular momentum. So I will start with the expression of HC, the integral of R minus RC plus V dm over the body. Okay, any questions before I continue? Questions? Okay. So what I'm going to do is I'm going to say that V is the velocity of some material point on the rigid body. So I can say that V minus Vc is omega, the angular velocity of the rigid body, crossed with R minus Rc, right? So R is the position vector of the point which has velocity V, Rc is the position vector of the center of mass. So V here becomes okay, so this V becomes equal to Vc okay, with me so far? Now I'm going to expand and split this into two integrals. I want to simplify these terms. How does the first term simplify? Right, so exactly. So Vc does not depend on dm, so I can take it outside the integral. So that's for the first term. And what is this integral equal to? 0, right? Why? Why is it 0? Exactly. It's the same as we did for a system of particles. When you're calculating the average distance from the average, you're going to get 0. Or you can think about it as this is the integral of over the body of R dm minus the integral of RC dm, which is going to be equal to 0. So this term is 0. Any questions? Just make sure your neighbor understands this, is okay with this. All good? No? What's the issue? Is it why this term is 0?
Yeah.
Okay, so first of all, I had this term, right? VC, the velocity of the center of mass, does not depend on the particular dm I'm considering, right? So I can take it outside the integral. Then I'm left with this term, r minus rc dm. I will expand it. It's the integral of r dm minus the integral of rc dm. Again, rc does not depend on the integral, so I can take it outside. So rc times the integral of dm is rc times the total mass. What about the integral of r dm? The integral of r dm is rc times the total mass. It's the top equation. rc is equal to the integral of r dm over the integral of dm, right? So the integral of r dm is rc times the integral of dm, or the rc times total mass. So these two terms are equal, so they sum to 0. And as your friend was saying, say I have two objects. Say I have two objects. Whatever, my backpack over there and this board over here. And I'm located at the center of mass between the two. Now, if I want to find the location of the center of mass of these two particles relative to me, I'm the new origin. The position vector of the center of mass is going to be the 0 vector because I am at the center of mass. So physically, what this is doing is calculating the center of mass relative to the center of mass. Okay. Any other questions? Now I want to simplify the other term, and for this I'm going to use the back cap identity. Have you heard of the back cap identity? Google it real quick. What is it? What does it say? Yes. So if I had A cross B cross C, that would be equal to what? Is that it? Do I have this right? So that's where the name comes from, back gap. Okay, so I want to apply it here. So I'm taking this integral, and I'm saying that the integral over the body, r minus rc, so it's going to be omega r minus rc dot r minus rc minus c, which is r minus rc, times omega dot r minus rc. dm. Okay. Take a few seconds, review, double check that I did this right. We don't want mistakes at this point. And if you think that this expression is okay, did you check it? Any questions, mistakes, anything? If you think that this expression is okay, now we need to think of a way to take omega as a common factor, or to take omega outside the integral. I can think of a way to do that for the first term, but what about the second term? For the second term, can I take omega outside the integral? you might want to use the definition of the tensor product. A bond B acting on C. Any ideas? How do we take omega outside? Maybe using the tensor product, definition of the bond product. Remember that A bond B applied to C is B dot C acting on A. So there are some similarities here. So how can I rewrite the last term here? In such a way that I can take omega outside the integral. So what would we get? Okay, so your friend is saying that I can rewrite this as R minus RC, bond R minus RC acting on omega. Is that right? That would be R minus RC dot omega along R minus RC. So I think it's right. Do you agree? Raise your hand if you do. Okay, there's some disagreements. Any questions? Questions? Okay. So this term I can write it like this, and this term I can also write it as the magnitude of R minus RC squared times the identity tensor times omega, right? Because the identity tensor times a vector is just the vector itself. So I omega is equal to omega. And the angular velocity is a property of the rigid body, right? It's a property of the whole rigid body. Does not depend on the particular point I'm considering. So it does not depend on dm. I can take omega outside the integral. So then this whole thing becomes equal to the integral over the body of R minus RC squared times the identity minus R minus RC bond R minus RC dm times omega. I would need to use I, so I'll call the identity tensor, I call it big 1. Identity. So what is this object here? Is it a vector? This object. Is it a scalar? Is it a vector? What is it? Yes. What is it? It's a tensor, right? It's a tensor. It's the difference of two tensors. It's a tensor. An integral of tensors is the sum of tensors is still a tensor applied to a vector, which gives us the angular velocity vector. Can anyone guess what we're going to call this tensor? No. It has to do with position vectors only. Any guesses on what we're going to call it? Yes. Yes, it's going to be the inertia tensor. I'm going to call it IC, the inertia tensor about the center of mass. Yes?
How is the first term, the one with the identity, how is that one also a tensor?
Because the identity is a tensor, right? And I'm multiplying a tensor by a scalar, which is the magnitude of 1 minus RC squared, which is going to be a tensor. Okay? So the heavier the object is, the more mass it has, so the heavier the object is, the more linear inertia it has, and the more difficult it is to initiate translation or change its translational motion. So again, if I have a heavier object, it's more difficult to move, right? So it's more difficult. This all is happening in terms of linear motion. So the more mass it is, the more linear inertia it is, the more difficult it is to initiate linear motion or to change the linear motion of the body. Now, the angular inertia here, it has to do with the mass distribution of the body, right? So what this is measuring is the kind of distance between all the points on the body relative to the center of mass. So if all the points were concentrated at the center of mass, the rotational inertia of the body would be what? It would be 0. If all the mass is concentrated at RC, R minus RC would be 0. And the farther away I am from RC, the more mass distribution I have, the greater rotational inertia I have, the more difficult it's going to be for me to rotate, right? So am I going to be more prone to rotation if I'm moving like this or if I have my arms out? So think about it. If you have a little kid, or when you were little kids and you were walking on a high beam, would you be more stable walking like this or walking with your arms out? Arms out. When you're walking with your arms out, you have the same mass, right? So you have the same linear inertia, but you have a greater rotational inertia. So your resistance to rotation is going to be larger. That's why when you have pole walkers, people who tightrope walkers, they're holding poles because they're increasing the rotational inertia so that tipping becomes harder. Okay? We'll watch, later on we'll watch videos of an ice skater. An ice skater that's rotating, can't do it, but when an ice skater that's rotating has their arms up, they have greater rotational inertia. When they pull their arms down, same mass, less rotational inertia, they're going to rotate faster. So the more spread out you are, the more spread out an object is, the more rotational inertia they have, the more difficult it is for them to rotate. So that's kind of an intuition for the inertia tensor. We'll get back to it. We're not going to stop here. But for more interpretation, what I want to do is I want to express the components of the inertia tensor, the matrix components of the inertia tensor. Okay, so let us do that. Okay, so I can say that HC is equal to IC omega, right, where IC is equal to the integral over the body of R minus RC times the identity squared minus R minus RC Notice that the inertia tensor only depends on the geometry of the body, right? It does not depend on the motion. Okay. Okay, so let R minus RC be x plus y plus z easily. So I have my rigid body, I have the center of mass, and I have my differential mass dm. And this vector here, R minus RC. Okay, what is the magnitude of R minus RC squared? Yeah. Okay, I have a question. Can anyone guess why I used a co-rotational basis to express R minus RC? Why did I use a co-rotational basis? Not a fixed basis to express R minus RC. Yes.
So you can find the moment of inertia relative to the body.
Yes. Yes, but think about it a bit further. You're close. Why did I use a co-rotational basis? To describe the mass distribution of a rigid body rather than some fixed basis somewhere fixed in space. Yes. Yes, the rigid body is moved relative to a co-rotational basis. If I put a basis fixed to me, the mass distribution relative to this basis is going to be constant, right? But relative to some other fixed basis is going to change, right? So we're going to see that the components of the inertia tensor on a co-rotational basis are fixed, whereas on a fixed basis somewhere else in space are not going to be fixed. So the components of this vector, and we'll do this. Okay, so basically I want to keep this right? Remember, we said that if we have a tensor, T, I can write it as the sum Tij Ei 1 Ej. Sum over I, sum over J. I equals 1 to 3. I'm going to write it there again. If I have a tensor, I can write it in this way, as the sum of one product. How many terms is that? I is going from 1 to 3, J is going from 1 to 3. How many terms is that? 9, right? I can go from T11, T12, T13, T21, T22, T23, T31, T32, T33. So that's 9 terms, okay? And if I have a vector U, the sum k equals 1 to 3, uk, ek, how many terms is that? 3, right? That's equivalent to saying u1, e1 plus u2, e2 plus u3, e3. So multiplying these two together using the definition of the bond product is equivalent to writing this matrix. So the matrix, the array Tu components of it are equal to T11, I need more space, T12, okay. So again, whatever vector that results in the multiplication of T times U, that's equivalently expressed in matrix multiplication, like this. I can actually do the bond product and get that result, calculate the matrix multiplication and get that result and show that they are equal. Okay? So remember, any questions about this? Questions? Yes?
Is the vector tu inside the bracket?
Yes, it's a vector, right? Because it's a tensor times a vector, which is a vector. Yes. Other questions? Okay. How did we represent the identity tensor? Does anyone remember how we represented the identity tensor in terms of bond products? How to represent the identity tensor in terms of bond products? Right, we said that identity tensor is EX bond EX or E1 bond E1 plus E2 bond E2 plus E3 bond E3. So I can write the matrix representation of the identity tensor as 1 0 0 0 1 0 0 0 1. So again, what am I trying to do? I'm trying to take this tensor okay, so I'm trying to take this tensor and express it in matrix form. So I know the matrix representation of, well, this is a scalar. X squared plus y squared plus z squared, identity matrix is that. Now I want to look at this term, the R minus RC bond R minus RC. Well, that's equal to XEX okay, take a minute, write the matrix representation of this tensor here. I'm happy to help if you have any questions, but try to do it yourself. Write the matrix representation of this tensor. I'm gonna pass by and check. Yeah, so you're gonna get 9 terms out of this because the EX is gonna bond with the 3, EY is gonna bond with the 3, EZ is gonna bond. Good start. Where are you working?
I haven't even started yet.
Why not?
I don't know how to tackle it.
Okay, so it's just like regular multiplication. You do x ex bun x ex, x ex bun y ey, x ex bun z e z, and then so on. You get 9 terms. And the ex bun ex term is the 1 1. The ex bun ey is the 1 2. The ex bun ez is the 1 3. That's how you place them in the matrix.
Thank you.
No. Exactly. Okay, good job. Yes, good start.
Essentially, check the
X squared, y squared, and z squared are correct, but the off diagonals are not 0.
Oh, I thought they were dot products.
No. So, no, they're not the products. They're x ex bun y ey. So there's xy ex bun ey. So you're going to have like xy here. Okay, done? Okay, great. Why is it a minus? Why do you have minus signs?
Oh, because I was like EX when I was doing like EY and EX, then I was thinking negative EC.
Oh no, it's just that you get ex bun ey, and that's it. Ex bun ey, and whatever the coefficient of that is goes in the 1 2 spot in the matrix. Yeah. Right, so that's equal to x squared ex bun ex plus, ex bun ex. Plus so on. So I can write this in terms of the matrix representation. Okay, so that's the matrix representation of this. Does that make sense? 9 terms total. Okay. So then, R minus RC times the identity minus R minus RC bun R minus RC is going to be x squared plus y squared plus z squared times the identity 1 0 0 0 1 0 0 0 1 minus this matrix. It is a symmetric matrix, right? So then that matrix here is equivalent to that's the matrix of representation of what's inside this integral, of what's inside the integral. So the components of IC, these are the integral of each one of these dm. So again, this is the matrix component, the matrix representation of the tensor which is inside this integral, this tensor. Okay, so the inertia matrix is going to be the integral of each of the individual terms. So the integral over the body dm. What is it? Yeah, d squared plus y squared. So this is the inertia tensor of a rigid body. So these are called the mass moments of inertia because they measure mass distribution. If you've taken mechanics of materials, then maybe you've seen area moments of inertia. Have you seen those? So instead of dm, you're going to have a dA. It's going to be the distribution of the area, kind of looking at the geometry of the problem. So this is the mass moments of inertia. It looks at the distribution of the mass. So for example, here, if I have a rigid body, 3 unit directions, Ex, Ey, Ez. What is this component looking at? This component here, the integral of x squared plus y squared dm, specifically. Which mass distribution specifically? The mass distribution about a specific axis, which is it? Exactly, the z-axis. Do we see it? So this tells us the mass distribution about the z-axis. So x squared plus y squared is the distance between all the points on the body and the z-axis. And you're summing, for every point on the rigid body, you're summing its distance from the z-axis times its mass. So you get the mass distribution about the z-axis. So here that's the mass distribution about the x-axis, mass distribution about the y-axis. Now the products of inertia, these, okay. So these terms have names. I see xx, I see xy, I see yy, I see zz, I see xy, I see xz, I see yz. And it's symmetric. Same thing on this side. I see yx and I see xy are the same. So these diagonal terms, they're called the moments of inertia. And the off-diagonal terms are called the products of inertia. Okay, so again, question. If I have a person standing like this versus a person standing with their arms open, and I'll take the easy axis to be like this, is the moment of inertia ICZZ greater for this person or for that person? Person A or person B? B. B has greater ICCZ, right? Because the mass distribution about this axis is greater. And we can see that this term is measuring the mass distribution about that axis, right? Okay, let us consider your phone. Like this. And we're gonna take a rotational basis on the phone. Call that EX, EY, EZ. Arrange in increasing order. That's the center of mass. ICXX, ICYY, and ICZZ. Go ahead, do it. Which one is the greatest? Which one is the least? Okay, can you think of a shape where all the moments of inertia are equal? A sphere, right? Can you think of a shape where two of the moments of inertia are equal? A cube, like a sphere, if the basis is oriented nicely along the cube, then the moments of inertia are going to be equal. Okay, so here, which moment of inertia is the greatest? Z, right? I have the most mass distribution about Z. What about which one is the least? Y, right? Does that make sense? Any questions? Okay. What is the product of inertia IXY for this shape?
0.
Why?
Symmetrical about the
Yes. Okay. So what is the product of inertia for this shape? C is at the center of mass of the body, so it's at like the middle in all thicknesses, kind of. Okay. So I xy about C. What's the formula for that? That's the integral of minus xy dm. Okay. Oh, one thing I need to say is that in Miriam Craig in the textbook, they call this term, instead of they calling it Ixy, they call it minus Ixy. So then Ixy would be the positive integral, not the negative integral. But we're not going to do that. Our convention is going to be to take Ixy to be the minus integral of xy dm. Okay? So going back here, the integral of xy dm over the body. So for all the points on the body, I'm integrating xy dm. Okay. xy. Let me add some dimensions here. Let's do A, B, C. Okay. What are the coordinates of this point? Or if I draw the vector here from the center of mass to this point, this upper corner here, what is it going to be equal to, this vector? Yeah, A over 2 EX plus B over 2 EY plus C over 2 EZ. Plus C over 2 EZ. What is it? Should I flip? Yeah. Okay, so there, B over 2. Yeah, A over 2 EY. So B over 2 EX, A over 2 EY. Okay, and C over 2. C over 2 EC. Okay, let us think 1 second. Okay. So yeah, I can split the, and if I look at a point here, what coordinates does this point have? Upper corner on the back. Position vector, I can write it as what? Minus B over 2 EX plus A over 2 EY plus C over 2 EZ, right? So what is this integral doing? This integral is going to sum, it's going to sum x times y for all times dm for all the points on the body. But you can think about it this way. I can divide the body into two. If I divide the body into 2 halves, all the points here and all the points there are going to have the same position vector, except the ex is going to be, component is going to be opposite. So whenever I have a point here and I'm summing the contribution to this integral, x times y, I have another point there with x minus x times the same y. So the contributions of these 2 points are going to cancel because of symmetry. So then what is the product of inertia integral of minus xy dm for integral over the whole body? It's going to be 0, because if I complete the integral, they're going to cancel out, it's going to be 0. So how can you can imagine though that if I change the axes, if I flip the axes in a different direction, I could change the axes in such a way so that the products of inertias are not going to be 0 anymore. I won't have these symmetries, okay? The general rule is that if the body is symmetric either about the x is equal, okay. If the body, if z is equal to 0 as a plane of symmetry of the body, then the products of, well, actually let's do it body by body. But anyways, what I was going to say is that you can imagine rotating the rotational basis so that the body is no longer symmetric. The products of inertia are not going to be 0. So the case where the products of inertia are 0, then the rotational basis is what kind of basis for the inertia tensor? What do you call the basis of a matrix which makes the off-diagonal term 0? The off-diagonal term is 0. So which makes the matrix diagonal. What do you call that basis? Which diagonalizes the matrix? Linear algebra, I remember linear algebra. Yeah, eigenbasis, right? So whenever the products of inertia are 0, then the basis you're looking at the gravitational basis and eigenbasis, the gravitational basis factors are eigenvectors. So you can always find an eigenbasis for the inertia tensor, or the matrix representation of the inertia tensor. Okay? Questions? Okay. We do not always need to calculate the components of the inertia tensor, so these integral components, we don't always need to calculate them by hand. For common shapes, they are present in tables. So let us consider, we can consider this shape that we were doing, the rectangular parallelepiped, and let us look at their bases and try to get their results. So I'm looking at the first page, last one. We want to get their results. We want to write the inertia tensor for the rectangular parallelepiped. Okay, this is it. Oh no, they drew the shape differently. Okay. 1, 2, 3, 4, 5. 1, 2, 3. Okay, and center of mass. They call it G, and we'll call it C. Okay, we have the y-axis like this. EY. They have the x-axis like that. EX and EZ. EZ. Okay. And we have the dimensions A, B, and L. Okay. So I want to calculate IXX above the center of mass C. How do I calculate IXX above the center of mass C? What's the formula for this? Here, right? So it's the integral over the body of y squared plus z squared, yeah. And hopefully the result I should get is 1/12 m a squared plus l squared, okay? So how do I evaluate this integral? I'm integrating over a three-dimensional body. I can express dm. If it's homogeneous, I can express dm as what? Yeah, density times volume, right? And the volume I can write as what? Remember your triple integrals from calculus? dx, dy, dz. Yes, so that's going to be a triple integral. Y squared plus z squared, rho, density per unit volume, dx, dy, dz. So what are the boundaries for dx? X goes from where to where? No, not 0. C is the center of mass. So x goes from this plane, x is equal to what? Negative b over 2 to b over 2. Okay, y is going from that back plane to the front plane. So it's going from where to where? And z is going from Right. So if I integrate dx, this does not depend on dx, so I'm just going to get the integral minus a over 2, a over 2, minus L over 2, L over 2, y squared plus c squared rho times b, dy dz. Okay, which is equal to the integral I'm integrating dy. So I'll get y cubed over 3 plus z squared y evaluated minus a over 2, a over 2, integral minus L over 2, L over 2, rho b dz. Right? Am I making any mistakes? So now we need to replace y. So that's going to be a cubed over 8, 1 over 3, minus a cubed over 8. So a cubed over 4 times 3, a cubed over 12. A cubed over 12 plus z squared a integral with respect to z, so that's going to be z and z cubed over 3 evaluated between minus L over 2, L over 2 times rho b. So that's going to be rho b L, a cubed L over 12 plus a L cubed over 12, which is rho a b L a squared over 12 plus L squared over 12. What is rho a b L? Density times a times b times L. Length times width times height is the volume, and times density is the total mass. That's the total mass of the body. So we got m a squared over 12 plus L squared over 12. Is that what we have? Yay, we got that answer. So it's not magic, we get them from these integrals. We can actually verify that the products of inertia are 0. So the product of inertia here is minus xy dm. I xyc is minus the integral of xy dm. So minus triple integrals of xy xy rho dx dy dz, same boundaries, minus b over 2, b over 2. So that's going to be x squared over 2y minus b over 2, b over 2. This would evaluate to 0. So the product of inertia is going to be 0. Good review of calculus? Yeah? Okay. So in sum, what is the inertia tensor? What is the matrix representation of the inertia tensor of the rectangular parallelepiped on this basis, passing by its center of mass? So if I want to write the inertia, the matrix representation of the inertia tensor of this parallelepiped here, I see matrix representation of the tensor. What is the xx term? Xx term. We can read it up from the table. And we just showed it. It's m right? What is the xy term? 0. xz also 0. All the products of inertia are going to be 0. But about the y yy term. And here. Okay. So this is the connection between the inertia tensor that we derived and the matrix and these tables, the components in these tables. So notice that for all of these shapes, they take the basis, the gravitational basis, to be along the eigenbasis. So for all of these shapes, the products of inertia are not are zero, but that's not always the case, because what we're going to consider later on is not just one rigid body or one simple shape, but a system or a rigid body that is a composite of these shapes. Any questions so far? Questions? Yes.
There's like I, Y1, Y1, Y2, Y2.
Great question. So do you notice this I, Y1, Y1, I, Y2, Y2? What does this mean?
Moments about axes that don't go through the center.
Exactly. These are moments of inertia about axes that are going, so they're parallel to the y-axis going through the center, but they're off-center. They're going through the other points. So you can see that the mass distribution about y1 is going to be different than that about y. Actually, the mass distribution about the center of mass is the least. And whenever you move from the center of mass, the mass distribution increases, and we can prove it. So if we have the mass distribution about the center of mass, we can calculate the mass distribution about, or the moment of inertia about any other point using the parallel axis theorem. Have we heard of the parallel axis theorem? Yes. So we can show it. Okay, let's see if we can do this in 10 minutes. Oops. Okay, while I'm doing this, you can have the moments of inertia. Just take them fast. Okay, now this one I need. In the notes, I do the example we just did for the rectangle. I do it for the circular cylinder. So you have some practice there. Okay, so the parallel axis theorem. So what I have so far is that HC is equal to IC omega. I want to use the parallel axis theorem to show that HP is equal to IP omega where IP, the parallel axis theorem, is this one. will start with that expression there. I want to express it like this and obtain IP. And that's going to be a relationship between the moment of inertia about the center of mass and the moment of inertia tensor about any point P. Okay, so starting with HP is equal to HC plus RC minus RP cross MVC. I can say that if C and P are two material points of the same rigid body, that VC minus VP is equal to omega cross RC minus RP. So here I can write that HC is IC omega plus RC minus RP cross M, VC is VP so what should I do next? Mm-hmm. So this term and this term are the same. How will I get this term into the inertia? I'm going to use which identity that we just learned about? The back cap, right? So that's going to be IC omega, okay, plus back cap, so B omega BA dot C, so RC minus RP dot RC minus RP back cap minus C RC minus RP times RC minus RP dot omega. Same exact steps as before, now I have to copy the other term. Okay, same exact steps as before. I can write this as omega times the identity tensor, and this I can write as a bond product, which makes that's equal to IP omega plus this term. Where IP is that. Okay. Notice in this expression, if I set P to be C, what happens? If instead of any point P on the rigid body, any material point P on the rigid body, I take the material point P to be specifically the center of mass. If I replace P by C, then I get HC is equal to IC omega and then RC minus RC. So this term cancels out, right? So that's the motivation behind writing this form. Okay. So this is the generalization of this for any point P. The above expression still holds also. Any questions? Okay. So if you look at set 18, at the bottom of the page, you can see the parallel axis theorem. So I went ahead, you have it in the notes also, wrote, and that's a good exercise for you, wrote the matrix representation of the, just the matrix representation of this operation. So this is the inertia tensor for the moments of inertia, ix, x, iy, y, I, z, z, it has this form. For the products of inertia, it has other forms. So I'm looking at equation 6 in set 18. How much time do we still have? Oops, we're out of time. Next time what we will do is we will apply the parallel axis theorem to the rectangular parallelepiped to double check that these two are the same. Please bring this paper, bring it with you all the time from now until the end of the semester. You're going to use it. The table with the moments of inertia, or have it ready with you. Okay? Thank you all for coming today. It was a hefty lecture. See you on Thursday. And I have office hours.